Today we're going to take a look at lesson 4.4. This is on page 174 of our book. 4.4 is really similar to 4.3, the last lesson we looked at. This is proving and applying the angle side angle and angle side congruence criteria. So the last lesson was talking about, instead of these two properties, it was talking about side angle side and side side side. So that type of, that type of concept, the way those two things work is very similar to this lesson. But instead of side angle side and side side side, they're talking about two different properties or two different congruence criteria, which is angle side angle and angle side. So if you understand the last lesson, this is going to be pretty much the exact same thing, but now we're focusing on two new congruence criteria. So example one, I was reading through this just a minute ago, and all right, sorry about that. Had a delivery and my dog started freaking out. So I can't really remember what I was talking about, but let's just kind of start from here. So again, we're just using angle side angle and angle side, pretty much redoing the last lesson, but now talking about that. Example one, when I was reading through this, it kind of looks a lot more complicated than what it's just trying to say. So let me try to simplify what they're trying to say here. So how many possible triangles can you determine? That basically means, can you find when given two angles in the included side of a triangle? So let's pause there and let's go to the answer. So for each unique combination of AB, which is the side, that's the bottom of the triangle, the measure of angle A, which is one of the angles, and the measure of angle B, which is the other angle. And that's what they told us, right? How many possible triangles can you determine when given two angles in the included side? Take a look. There's angle A, there's angle B, and the side that connects them, right? That's really important when you're dealing with angle side angle. The two angles, it could be any two angles on the triangle, but the side has to be the side that connects the two angles. Super, super important. So for each unique combination of a side with two angles, there is a unique triangle. That means that it will specify, it will give you only one triangle. So what they're trying to say is, if I'm given two angles and the side that connects them, this triangle can only be shaped one way. It's not like I could have a really big triangle, a smaller triangle, a different shaped triangle. Just given those three pieces of information, the two angles and the included side, the triangle is determined. It's given. And that's what they're trying to get at here. So they're saying, let's create three different situations. So they're saying, let's create a triangle with a 68-degree angle, a triangle with a 57-degree angle, and a triangle with a 45-degree angle. And here's those three triangles. The given, or the thing that has to be there, is angle A is 25, and that's true in all three cases. The side length of AB is 3, which is true in all three cases. But angle B is what changes. They're just giving you three random examples. You could pick any other angle if you'd like to. What they're saying is, if I have angle 25, that angle A is 25, angle B is 68, and the side length is 3, that triangle is locked in place. It's not like this triangle could look differently. It's not like this triangle, the other angles and the other side would be different. Once you assign two of those angles in that side that includes those two angles, that triangle is locked down. You have one specific triangle. You can't create a different type of triangle. That's what they're trying to get at there. Top of page 175, this is talking about theorem 4.8, or I'm sorry, theorem 4.6, angle side angle, which is basically the definition of angle side angle. Again, make sure that you understand, for angle side angle to be used, right, to use that congruence criteria, it has to be any two angles inside your triangle, but the side has to join those two angles. So in this case, if I'm talking about angle N and angle M, I have to use that side MN. I don't have a choice. Take a look over here. If I use angle S and angle T, I can't use for my side, I couldn't use RT, right? Because it's not joining those two angles. The side has to join the two angles. So really, really important for you to understand that. Example 2. Prove. We're not going to do this. Again, this is just a mathematical way that you can say LMN is congruent. It's the same triangle as RST. So it starts off with some given information. This is what it wants you to prove. It wants you to prove that the two triangles are congruent. And very similarly to another lesson, I don't remember when we talked about that. Maybe it was 4.3. Seems like forever ago. What they're doing here to prove it is they're using rigid motions. They are translating triangles. They're basically moving these triangles around the page. They're rotating them. You can reflect them. You can do these rigid motions, and you could have that triangle go from here down to here, right? And then they're rotating it. So that triangle goes from down below and it rotates up above. And then they're reflecting it across that line to basically make that bottom half lay right on top of the top half. So by using those rigid motions, very similarly to that example in 4.3, by shifting it around the page, translating it, by rotating it and reflecting it, those two triangles lay right on top of each other. They're the exact same triangle. So if you want to use rigid motions, you can, but they're using rigid motions just as a way to prove angle side angle. If you have two angles with the side that joins them, if that's congruent, if that's the same as two other angles with the side that joins them, you could say that those two triangles are congruent. But if any problem references example 2, we are not going to do proofs in this section. Example 3. Apply angle side angle. So a technician installs cables from a cell phone tower, so that's this right here, to the ground. To pass inspection, both cables must be the same length. Does the installation meet the cable length requirements? Explain. So here they're using angle side angle. What they're emphasizing here is the two angles. The top, they're both 52 degrees. So I know that that angle in both of those triangles are the same. I know that the side is the same because the side is literally the same pole, right? It's the tower. So the side length has to be the same because it is itself, right? It's the same exact thing. And then the other angle that joins, right? The two angles in the side, the other angle is 90 degrees. So that tells me that both of those angles are 90 degrees. The side length is exactly the same because it's literally itself, right? There's not two different side lengths here. It's just one item. And then the top two angles are the same. So that means because of angle side angle that those two triangles have to be exactly the same. And like we've talked about in the past, something called CPCTC. Let's see if they have it on here. Yep, right here. So CPCTC is just a fancy way of saying congruent parts of congruent triangles are congruent. So what that's saying is if I just used angle side angle to prove that these two triangles are the same, that they're congruent, that means every part of this left triangle has to map to every part of the right triangle. So the base has to be the same length for this triangle as this triangle. The hypotenuse, that cable, has to be the same length for this triangle as that triangle, right? The angle down here at the bottom, that has to be the same exact angle as this angle. So once we prove that these two triangles are congruent, you can basically map everything that's corresponding and say that those are congruent as well. Example 4, investigate the angle side. So the last 3 examples talked about angle side angle. Now they're talking about angle side. So given triangle ABC, is the triangle determined by angle A and angle B and the non-including side and the non-included side AC unique? So they're saying there's A, there's B, and the non-included, which means it's not the side that's connecting those two angles, it's one of the two other sides. So after taking a look at this problem, again, some of the wording can be a little bit confusing, like given triangle ABC, is the triangle determined by? So determined is kind of a unique word. It doesn't really make sense. It's almost like you'd think there's a typo. But I'll put that in, language that kind of makes sense here in just a second. So given triangle ABC, is the triangle determined by angle A, angle B, and the non-included side AC unique? So what they're saying is ABC unique compared to DEF, or are they the same? So are they different triangles or are they the same triangle? Short answer, they are the same. And you can see that just by using the angle side congruence criterion. Notice there's two of the angles that match up. So angle A matches up with angle D. Angle B matches up with angle E. The way I know that is that's one tick mark, that's one tick mark. That's two tick marks, that's two tick marks. So that tells you how they correspond with each other. And then side AC is the same as side DF, again, because of those one tick marks there. So that is the definition of angle side. As long as you have two angles and a side that's not included, that's angle side. So just based off these pictures, I would say that the triangles are not unique. They're exactly the same. This triangle is not unique compared to that triangle. Those two triangles are exactly the same based off of angle side. So let's see what they're talking about here. Assume that it is not unique, basically saying then there must exist a triangle DEF such that ABC is not congruent to DEF. So assume that they're not. So by the triangle angle sum theorem, this is just a lot of algebra to say this. We know that A and D are the same based off of those single tick marks. We know that B and E are the same based off of those double tick marks. So what we need to find out is if C and F are the same. Well, if you think back to what they call the triangle angle sum theorem, that basically says that each triangle has to add up to 180 degrees, right? No matter what the triangle looks like, there has to be 180 degrees inside of it. So if both of these triangles have 180 degrees inside of it, and they both have the same angle A and D, they both have the same angle B and E, well, then by process of elimination, C and F have to be the same as well, right? If I take triangle ABC and I start off with 180 degrees, I subtract angle A, subtract angle B, I'm left over with C. Same thing with DEF. If I subtract angle D, subtract angle E from 180 degrees, I'm left with angle F. So they have to be the same value. All three angles have to match. So C has to be the same angle as F. And that's basically what this paragraph is saying here. Just a lot of confusing algebra to say that. Therefore, by angle side angle, these two triangles are congruent. So since C is the same thing as F, now I have A and D the same, C and F the same, and side AC is the same as side DF. So using those three pieces of information, I have angle side angle, angle side angle. So therefore, by angle side angle, the two triangles are congruent, and the assumption is false that they're unique. A unique triangle is determined by angle A and B and the non-included side AC. So they kind of went away from angle side here and talked about angle side angle, but either way, you'd use that same congruence criterion to kind of look at those two pictures or those two triangles and figure that out. Theorem 4.7. Angle side. So here is just, again, the definition, basically saying as long as you have two angles in one triangle that correspond to two angles in another triangle, and the side that does not include those two triangles, because you wouldn't want to have side UV. That's not angle side, that's angle side angle. So the only side you couldn't use is UV. You could use VW, you could use UW, it doesn't matter, but just not UV. So two angles with a non-included side. Same thing over here. You have two angles with a non-included side. So that is the definition of angle, angle, side. Example 5, use congruence criteria. Here's an example where these triangles, you have angle, side, angle, angle, side, angle. So that is congruent by angle, side, angle. Just keep in mind with angle, side, angle, it's the two angles with the included side, the side that connects the two angles. Okay. Over here, you've got two triangles. You've got one leg is one tick mark, a second leg is two tick marks, a third leg is three tick marks. So by side, 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 those things have to be the same. Here you've got two angles that are the same, one tick mark, two tick marks, two tick marks, and it looks like a non-included side, right? It's not the side that joins those two angles. It's one of the sides that does not join the two angles. Same thing up here, one of the sides that does not join the two angles. So you could say that those are congruent by angle, angle, side. In this case, they're saying that this top left of the triangle is the same as this top left of the triangle. The base of the triangle is the same as the base of this triangle. But the thing that throws you off is they're saying that this angle, the bottom left angle, which should be this angle here, they're saying that this angle is the same as the opposite angle, right? This would be angle, side, angle if that angle was this part right here. But they're including a different piece of information. Based off that information, you can't assume anything. You can't just say that these two triangles look the same, so they should be congruent. You have to go off of the given information. So based off that information, you cannot determine if those two triangles are congruent. Okay, so this is just example 5 continued. So when we were just talking about congruent triangles, this is just going into a part B saying prove that side length FH is congruent to side length JL. So is the bottom the same length as the bottom of this triangle? We're not going to talk about the proof part of it, but you could determine that yes, they are based off of angle, angle, side. Because again, if you look at these two triangles, F corresponds with J, G corresponds with K, and GH corresponds with KL. So I could say that those two triangles are congruent. And because of CPCTC, corresponding parts of congruent triangles are congruent, because of that property, I could say that FH is the same side length as JL. But again, we're not going to go through the proof part of it. Example 6, determine congruent polygons. So all sides and angles of ABCD are congruent to the corresponding sides and angles of its image. Is ABCD congruent to its image? Let's take a look. So let's look at the top left triangle, ABC, and then A prime, B prime, C prime. Well, it looks like that triangle has a side that's 3. This triangle has a side that's 3. Angle B is the same as B prime, and side length AB is the same length as side length A prime, B prime. So because of that, side angle side, I can say that this triangle is congruent to this triangle. Let's look at the bottom right hand. So this littler one down below. Looks like CD is the same as C prime, D prime. Looks like D is the same as D prime. And it looks like AD is the same as A prime, D prime. So based off of that information, again, I have side angle side, side angle side. So I can say that those two triangles are congruent. Since that is true, you could again use that, I think it was example 2, where they took that, this polygon and they shifted it around the page, they translate it down over and they lay right on top of each other. But once you prove that those two triangles are congruent with these two triangles, all parts of that triangle have to be congruent. Remember, CPCTC, if I say that ABC is congruent to A prime, B prime, C prime, What I'm saying by that is that the side length AC has to be the same exact side length as A prime B, A prime C prime. Okay, once I prove that these two triangles are congruent, then all parts of those triangles are congruent. So everything is given with the exception of AC being the same length as A prime C prime, but because I proved that those two triangles are congruent, I know that all parts of those two triangles must be congruent. So AC has to be the same length as A prime C prime. So on page 179, we're up in the concept summary. Again, two main ideas from this lesson, angle side angle and angle angle side. Just keep in mind, if you want to use angle side angle, you can pick any two angles in that triangle, but the side has to be the side that connects those two angles. And then for angle angle side, again, you could pick any two angles in that triangle, but once you do, the side cannot connect those two angles. So in this case, you could pick U and V for my two angles, but I could not use UV as my side. I could use VW, I could use UW, but I could not use UV. That would not be angle angle side. All right, now we're on page 180. This is the practice problems. Looks like there's only, there's only 5 problems. We're actually going to skip 16 and 17 because those are proof problems. We'll probably talk about them and just see if it follows one of the congruence criteria, but we're not actually going to write out a proof. So number 15, this looks a lot like that example 3, which was the cell phone tower with the cables that come down to the ground that we talked about a minute ago. Carpenters build a set of triangular roof supports, each with the measurements shown. How can the carpenters be sure all the slanted beams are the same length? So how do you know that these two sides are the same length? So it's pretty much exactly like example 3. What they're doing is they're giving you that top angle is 28 degrees inside each of those triangles. They're giving you that this bottom part, right, the bottom part of that vertical thing is 90 degrees. Well, if the left side has to be 90 degrees, the right side also has to be 90 degrees. I don't think we talked about that in the last problem. If this is a straight line, right, we know straight lines have 180 degrees. Well, if the left side of that beam is 90 degrees, 180 minus 90, that means that the right side has to be 90 as well. So what they're hinting at, I think, on this problem is angle side angle. You have that top angle, you've got the side that joins the bottom angle, which is 90 degrees, right? 28, the side length, 90 degrees. The top here is 28, the side, and 90 degrees. I think this is going to be, these two triangles are going to be congruent based off of angle side angle. Remember, if this triangle and this triangle share this side, right? This side right there in the middle, it's the same side that both triangles use. So it has to be the same. So we have angle side angle. Because of angle side angle, I know these two triangles are congruent. And because of CPCTC, congruent parts of congruent triangles are congruent, I know that all parts of this triangle, all 3 angles, all 3 sides have to be congruent. They have to be the same to all 3 angles of this triangle and all 3 sides of this triangle. So that tells me that the slanted beam on the left has to be the same length as the slanted beam on the right. Number 16, prove angle angle side. So again, this is talking about a proof, but looking at this based off the information given, it looks like it's angle angle side. There was an example that talked about this. If PQ if they correspond to ST, then angle R has to be the same as angle U, which means all 3 angles are the same in each of those triangles. Then you have angle side angle, which ultimately proves angle angle side. So again, if you really want to see that thing worked out, send me an email. I can work it out and send you a picture, or I can meet you on Zoom and walk you through it. But it's not terribly complicated, but because we've skipped proofs for so long now, we're not going to include them in these lessons. Number 17, write a proof. So given this information, prove that AX is congruent to CX. So prove that that side of that triangle is congruent to this side of this triangle. And what they're doing here is they're using angle, angle, side. And let me show you why. These two angles right here, those two angles are vertical angles. That means that they are equal to each other. So once you know that they're vertical angles, you know you have angle C is the same thing as angle A. Angle X is the same thing as angle X. And then side length BX is the same thing as side length DX. So once I know that, I've got angle, angle, side, basically proving that those two triangles are congruent. Once I know they're congruent, I know CPCTC is in effect, so I know that this side length has to be the same as that side length. Number 18 is ABCD congruent to GHJK. So I think we had a problem. I think it was example 5 that talked about this. Basically giving you some weird shapes, but within those weird shapes, they're giving you two triangles. So the idea here is to check and see, are these two triangles congruent with these two triangles? If so, then yes, they're congruent. So let's take a look at it. Triangle ADC or ACD, whatever you want to call it. This triangle down here, the bigger one. Let's start off with the bigger one. That triangle there, I think what they're trying to get at is going to be congruent to this triangle here, GKJ. Looks like angle CAD, basically this angle right here, is the same as JGK, because you can see they're both two tick marks. Looks like angle D is the same thing as angle K, because they both have 3 tick marks. And then side length CD is the same thing as side length JK, because again, 1 tick mark. So because of that, I can say with confidence that ACD, that triangle, is congruent with GJK, whatever you want to call it, right? These two big triangles are congruent. Now that I know that, let's check and see if the smaller triangles are congruent. Looks like BC is 2 tick marks and HJ are 2 tick marks. So those two sides are congruent. Looks like angle BCA, that 1 tick mark right there, that's the same thing as angle HJG, because there's 1 tick mark right there. And then I think the last thing is going to be this side right here and this side right here. Because these two triangles are the same, right? The two bigger triangles, we know that all parts of those two bigger triangles are the same. So I know that AC is the same length as GJ, right? They have to be. So that means those are, I just put 3 tick marks there. So now I have side angle side, side angle side. So I've proven that the smaller triangles are also congruent. Well, if these two small triangles are congruent and if these two big triangles are congruent, that means that the ABCD has to be congruent to GHJK. Number 19, go and clean up my mess up here. I don't want to draw on this book. If ABCD is congruent to EFGH, are all corresponding parts congruent? Explain. So what they're saying here is if I have shown it's given that ABCD is congruent to EFGH, this shape is congruent to this shape, yes, all corresponding parts are congruent. Based off of CPCTC, corresponding parts of congruent triangles are congruent. If I took these two shapes and I created 2 separate triangles here, there's other ways you could have done that, right? I could have joined BD and HF, you know, it doesn't matter. But if these two shapes are congruent, then I can say, I'm basically working backwards from this example. Then I could say that this bigger triangle is congruent to this bigger triangle. This little triangle is congruent to this little triangle, which means that all parts of that shape are congruent with all parts of that shape because of CPCTC.